Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows. I am pursuing my PhD in organic synthesis from either Badampur. So I am the TA of this course named Retrosynthesis in Organic Chemistry, instructed by Professor Shamik Nanda from IIT Kharagpur. So in this class we discuss some questions based on this topic, which you have by solving these questions will help you to attempt the upcoming assignments and understand more about this topic. So let's start. So today we'll discuss about Wittig reaction and solve some questions based on that, so that in future whenever you get some question on this topic you get an idea and solve easily. So it is an organic reaction where an aldehyde and ketone are heated with phosphorus ylides to produce a alkene. So there are two components of this reaction. One is carbonyl compound, but specifically aldehydes and ketones, and another component is an ylide. The thing is, by this method you can't form alkene from any ester or amide. For those type of substrate you need a different type of reaction, though that we will discuss in the next class, that is called Tebbe reaction. So by using that one you can perform olefination of the ester and amide, but by Wittig reaction you can make olefination of this aldehyde and ketones. So what is the purpose? So here you can see, by using one ketone or carbonyl compound and an ylide. So what is ylide? Ylide means any bond which contains a partial positive charge and a negative charge adjacent to each other. That is called ylide. And this is so we are writing this way, but it can also present in the reaction mixers like this way. This is called ylide, phosphorus ylide. Okay, so what is ylide? Now you know, whenever you see two adjacent charge, that will be ylide. Now what happens? By this reaction we get a alkene. So here we can form a carbon-carbon bond between 2 and 4. So 4 is coming from this ylide and 2 is from the carbonyl compound. So the elimination of this part. Okay, just imagine the upper part is totally eliminated and this lower part are getting connected with each other. Now if we look into the mechanism, what is the mechanism of this reaction? First, this ylide carbon, which is the negatively charged carbon, attack this carbonyl carbon and it opens up, forming this betaine intermediate. In the next step, this O minus again attack this phosphorus vacant d orbital. Phosphorus take up the electron from the oxygen into its vacant d orbital, and by this it forms this oxophosphetone intermediate. After that it undergoes a ring breaking through, like that this bond is coming here and this one is going here, electrons, and through this bond breaking we can get this alkene with elimination of this byproduct. Okay, so this is the mechanism of the Wittig reaction. So so there is some specification. Now if you want to form specifically a Z double bond or a E double bond, like the trans double bond or a cis double bond, just by changing the nature of the halide, changing the nature of the phosphorus halide, we can specifically get a stereochemistry of the product. That is, we can get a stereospecific product by using different halides. Now you can see whenever the halides contain a electron donating group, when this halide carbon contains any electron donating group, suppose this alkyl group has some plus I effect. So if this carbon contain any electron donating group, it specifically or selectively gives cis double bond in the reaction mixture. See, here the C double bond is greater in comparison to the E double bond. But when there is any electron withdrawing group on the halide carbon, that in that case we get specifically E double bond. We get in that case a E double bond. See how E and Z can be determined, that we know. I think along this double bond, if the higher priority groups are in the same side, that will be Z. If the higher priority groups are in the opposite side, that will be E double bond. Okay, so just by changing the nature of the phosphorus halide, we can get a stereospecific alkene as our product. So let's solve some question based on that. So they have asked provide the structures of this product. So first, this is a phosphorus halide. You can imagine if we break this bond like this way. This is a phosphorus halide because here will be a negative charge and there will be a positive charge. Now they have added this phosphorus halide into a aldehyde. So what will happen? Obviously Wittig reaction. Now after that, in the next step, they have added H3O plus. Now what will be the product? I am giving just 10 seconds, just give it a try. I will give the option because from option we sometimes exclude the probable one and all. Just give it a try. I just give 10 seconds. Okay, so now you can see on this halide, now it is electron withdrawing group or electron donating group. So this is a alkyl chain, this is a alkyl chain, so it's not any functional group or containing minus I effect or anything. So this will obviously give a plus I effect, that is a electron donating effect. So this is a stable halide. This is a stable halide. Okay, now what will happen? Obviously, as you know, in case of stable halide, what we get? We get a cis double bond. So let's try to draw the product. Now it's a acetal. You can see this is a ketal type of. There is a sorry. This is a acetal because there is a H. This is called an acetal. This group is called an acetal group. So in presence of acid, this is always a acetal groups are acid sensitive. Acetals are highly acid sensitive. So whenever we add acid into a acetal moiety, what will happen? This will open up by taking this oxygen will take up proton, get positively charged, then a lone pair of electron moves here and this open up. After that, so this bond will break and again another molecule of water comes. If we just draw it, I'm just drawing this as a AR. Now what will happen? After that, this is already positively charged. Then after that, now it is there is a water also because it is 3 plus. So the medium water will attack at this position. This opens up. After that, now again this oxygen goes here. This eliminates from the system. So for me, what will be the product? So product will be AR with a newly formed double bond. Okay, so this will be our product. Next question is draw the product of these intermolecular Wittig reactions. You have to draw the intermolecular Wittig reactions. Just give it a try, then we will solve it together. So what will be the answer? So there is already a Wittig salt is there. If we talk about the first one, there is already a Wittig salt, so this is negatively charged. So what will happen? This negatively charged Wittig will attack to this carbonyl compound. This will open up. what will happen? This will open up. After that, what will happen? Similar to the Vedic, this one will attack here and it undergoes a ring breaking, forming a double bond at this place. So what will be our product? The product will be this one. Okay. So this one will be our product. Now here you can see in this case a carbonyl compound is given but only bromine is given, not no PPS. Now they have already given the PPS as reagent. So from there you can get an idea that you have to prepare the ylide in medium, then that will react with the carbonyl compound. So what will happen? So this PPS phosphorus lone pair will attack to this bromine center, carbon center, and the bromine will eliminated, forming this ylide. Forming this ylide. Then when we are adding a base, it will deprotonate a proton from this position. When you are adding a base, it will deprotonate one proton from at this position, as it is adjacent to phosphorus, so this negative charge can be stabilized through resonance. So after that, this negative charge will react with this carbonyl center. Then it will undergo the cyclization. After that, through ring breaking, it will form this double bond. Okay, understood? think it was easy. Let's go to the next question. So there is two synthetic routes are given to form a single product. Now which route will be more efficient? Both are going via Wittig reaction. In one case, the Wittig salt is the CH3I. Another case, the Wittig salt is prepared from the cyclobutane halide. Now which one will be the more accepted one? So what will happen? In this case, first this PPH3 will react with this halide center forming this halide. Now by addition of base, a negative charge should be formed here so that you can form a halide. Now we know that this is sp3 hybridized and as well as cyclobutane. So there will be the negative charge on this position is not that much stable. But instead of that, when in this case the halide is this one. Which is the negative charge is far more stable here, so it is prone to react with our cyclobutanone forming this alkene, whereas this is not that much favorable to forming our desired product. Okay, so the favorable route will be the route 2. Let's go to the next question. So here we have already discussed about the stable halide and unstable halide. Whenever there is a electron withdrawing group on the halide carbon, that will give specifically E double bond, and whenever there is a electron donating group on the halide carbon, that will give specifically a Z double bond. Now from that one you just take the idea and try to solve this question. Okay, let's try. Now see, in this case the halide carbon contains a ester group CO2Et. So therefore ester group has a minus I effect and as well as minus R effect to stabilize the negative charge. So this is a stable halide. What will happen, as this is a stable halide, this will react with this carbonyl center forming a E double bond. So everything will be same. So what will happen? A E double bond will form, and this carbon has a CH CO2 it. Now in this case, okay, so this will be our desired product. This can attack at this position, but it's not possible as it's not alpha beta unsaturated double bond because there is a CH. Now this is also a stable halide and it will form a trans double bond. So the one is methyl, okay. This will be our product. Our next topic is another topic for olefination reaction is Peterson olefination. We have talked about Wittig olefination. Now next is Peterson olefination. What is the difference? In case of Peterson olefination, we are using a phosphorus halide. In case of Wittig olefination, we are using a phosphorus halide. Whereas in case of Peterson olefination, we will be using a silicon halide. We will be using a silicon halide. So reaction involving the addition of a silyl carbon ion to carbonyl compound to form a beta-silyl alcohol followed by elimination of silyl yields an alkene. Such a reaction is called Peterson olefination reaction. This is also known as Peterson elimination, Peterson reaction, and sometimes Peterson alkynation or alkynation. So what is happening? Here they have added a carbonyl compound with this silicon halide type of reaction, silicon carbon ion, because there is a carbon ion in now this can react with this carbonyl compound forming this beta hydroxysilane, because this is alpha beta, forming this beta hydroxysilane that will undergo elimination when through acid or base forming this alkene. So this reaction can be catalyzed by acid as well as by base, but by changing the catalyst we can get different stereochemistry of the product. How it's possible? Just let's see. So in case of beta base catalyzed reaction, the reaction going through a cyclic transition state. In case of base catalyzed reaction, base deprotonates this proton, it generates this O minus, they undergo cyclization. After the ring blocking, for this cyclic state, forming this cyclic state, OH and silicon should be seen to each other. So it will always undergoes a seal elimination and give this as our desired product. So if these are one that will undergo the cyclization. Through elimination it will give this type of product. But in case of base acid catalase reaction, this is undergoes an anti-elimination type of pathway, where this OH get protonated first, forming this OH2 plus. Now to eliminate this OH2 plus from the system, that has to be anti with the silicon group. So it should be anti, so that this bond rotates and this OH become, or the silicon becomes anti to the OH2 group. After that it undergoes an anti-elimination, forming this as a product. So if second this is R1, this is R2, after this rotation what will happen, this R1 comes here, see in this case the stereochemistry from the transition state has been held because it is totally seen elimination. But here there will be a twist because of this, see, carbon-carbon bond rotation. Is R1 comes here, okay. So just by seeing the stereochemistry of the product, or just by seeing the reaction condition, we can determine what will be the stereochemistry of the product. Okay, I hope it's clear. So whenever we will get a Peterson elimination, we just have to, by silicon we can get an idea, okay, this will be a Peterson elimination. But we have to check the reaction is going via a acid condition or a basic condition. If it's acidic condition, the reaction there will be an anti-elimination. If it's a basic condition, there will be a seen elimination. Now let's solve the question. So they have given two reactions. In both of them, what is given? Now the condition, you have to check the they have given trifluoroacetic acid. So that means the acidic condition. Both of them, these are acidic condition. So for there will be a anti-elimination. There will be a anti-elimination. Okay. So let's give it a try. You have to find the anionic center which will attack to this carbonyl compound, because they haven't showed it. You have to find which will be the anionic center. So here the lithium is connected to this carbon, so obviously this will be the negatively charged. This will be partially negatively charged. So what will happen? This negatively charged carbon will attack to this carbonyl compound. So this undergoes anti-elimination. Both are anti already, and there will be a double bond here. So what will be the product? The product will be product will be this one. Now in this case, what will the negatively charged carbon is this one, and that will attack to this carbonyl group again. And if we keep this one as R, this total part I am considering as R. Now what will happen? This opens, okay. Then after elimination, after protonation, it will be OH2 plus, it will be eliminated, and you will get this as our product. Okay, I hope it's clear. Let's jump to our next type of olefination reaction, which is called Julia olefination reaction. What is the difference from the previous two? In case of Wittig, it was phosphorusylide. In case of Peterson olefination, it was silicon carbonate. In case of Julia olefination, it will react with a sulfone. The ketone and aldehyde will react with a sulfone in presence of base to produce an adduct which is treated with an acetic anhydride, gives acetyl derivative and undergoes a reductive elimination, and it is presence of sodium amalgam, and it will yield alkene. In case of Julia olefination reaction, we selectively get a E double bond. Like in case of beta olefination reaction, just by changing the condition of the reaction, you can get E and Z. Similarly, in case of Wittig reaction, just by changing the nature of the elide, you can get E and Z. But in case of Julia olefination, irrespective of what you are using, you will just get E double bond. Okay, so if any reaction is given where you have to form a E double bond specifically, and you can't change the reagent, you can't control the reaction condition, then what will go, then which will reaction you will perform? You will just perform this Julia olefination reaction. So what is happening here? So in presence of butyl lithium, this proton will be abstracted, forming a negative charge here, that will react with this aldehyde center and form this alkene. So this is the mechanism. If we go step by step, what is happening? As I said, this butyl lithium will take up one proton from this position, forming the carbon ion. Then this carbon ion will attack to this aldehyde center, forming O minus. After that, if you add acetic anhydride, this O minus will be acetylated, giving us this intermediate. And when we add sodium amalgam, it will give single electron to this sulfur atom, break this bond through forming this. Then again, by using another molecule of sodium amalgam, that will trap this oxygen and form another single electron, and these two single electron undergoes a coupling, forming this E double bond, forming this E alkene. So in case of Julia olefination, we get a specifically E double bond. Okay, So the mechanism is quite different, but the last part is quite different, but the beginning is quite same with that VTIC. It is just attacking, then it is get acetylated. Instead of elimination via this sulfur is eliminated separately, forming a radical here. This OAC gets eliminated by forming a radical here. Then that two radical undergoes a coupling, give us this E double bond. Now let's try to solve this one. Butyl lithium is given aldehyde and acetic anhydride. So what will happen? It will undergoes Julia olefination reaction, because in the next step sodium amalgam is given. So you have to predict what will happen in the first step, then what will happen in the second step. So you have to determine the intermediate, the hydroxy intermediate. Let's give it a try. So this will, butyl lithium negatively charged, will take up a proton from this position, forming a negatively charged sulfur. This undergoes a reaction with the aldehyde. Which undergoes acetylation. So what will form? This will be our intermediate form here. So the what will be our A? So this one is our A. Then by using sodium amalgam, what will get? We'll get, by the similar mechanism, we'll get a E double bond. Okay, it was easy. Now then try to solve this one. So there is a sulfone is given, and they have given a compound. So here you have to check there is a aldehyde center is there, and sodium HMDS is a base. Is a base in presence of base. So what will happen? It will undergoes a Julia olefination. Just give it a try, then we'll solve it. It is easy. So what will happen here? by using base. These protons get deprotonated, forming this negative charge here. I am not drawing this part, I am just drawing this as AR. Okay, now what will happen? It will attack to this carbonyl center, and we know it will specifically give a E double bond. So if it attacks, so this one will be okay. So after the elimination, we'll get this type of double bond. So here this group will be there, I am not drawing, and here the other ethyl and OC. Okay, so here the double bond will be formed. Let's go to our next topic, that is Johnson-Claisen rearrangement. I have seen last assignment where there is a question of Johnson-Claisen rearrangement. So what is Johnson-Claisen rearrangement? We know about Claisen rearrangement. This is a 3D sigmatopic reaction. But what is Johnson-Claisen rearrangement? So it is an organic reaction where an allylic alcohol is heated with an trialkyl orthoacetate under mildly acidic condition to produce a gamma delta unsaturated ester. A gamma delta unsaturated ester. So what is the mechanism of this reaction? First, the reaction begins with the protonation of an alkoxide group of orthoacetate The reaction begins with the protonation of one of the alkoxide group of orthoacetate. So one of the alkoxy group will be protonated. After that, what will happen? Then another alkoxy, this electron will come here and this eliminates from the system. So as protonated alkoxide is then released as the molecule of the alcohol, and forms an oxonium cation, and it forms a oxonium cation. Then the allylic alcohol will attack to this oxonium cation, forming this intermediate, and through deprotonation and protonation another molecule of alcohol will be eliminated and forming another oxonium cation. Then again through deprotonation of this CH3 of this sp3CH bond, we get this 1,4-diene intermediate. We get this 1,4-diene intermediate. Then after that, what will happen? It will undergo a 3,3 sigmatopic reaction, because this is 1 1. So it undergoes a 3,3 sigmatopic reaction and forming this gamma delta ester, gamma delta unsaturated ester. Okay, so this is called Johnson-Claisen reaction. So whenever from a allylic alcohol or from any you are getting any gamma delta unsaturated ester, you will think about this Johnson-Claisen rearrangement. Okay, so if in a retrosynthetic pathway, suppose in a as a product you have given as a gamma delta unsaturated ester. So what type of retrosynthesis you will think about? You will think about this Johnson-Claisen rearrangement. Okay. So here I have given one question. This is option A. So which will be the product of this reaction? Which will be the product of this reaction? Just give it a look to this mechanism. Just try to understand this, then it will be easy for you to solve this one. Okay, let's go. Just give it a try. I give 5 seconds. Okay. What will happen? So as you know, in presence of acidic condition, one OMe will be eliminated by the help of another one. So this will be eliminated in presence of acid, forming this one. Now this allylic alcohol will take here, and this opens up. Okay. After that, what will happen? then this proton get abstracted and this eliminated in acidic condition, forming this forming this. Then it undergoes a 3,3 sigmatopic reaction. So that this comes here. So this bond breaks. Okay. So what will be the product? So in our product there should be a NME2. So in our product there should be a NME2 group. So there should be a NME2 group. So the product will be this one. So our product will be a amide. So the correct option is option B. Okay. So this much for today's class. So in this class we have discussed 4 name reactions which may help you to form carbon-carbon double bond, and another the last one we discussed where we can how the esters can go undergoes as a rearrangement. So in the next class we will discuss about some more name reactions which may help you to understand the retrosynthesis. So first we discussed about the Wittig reaction, then their mechanisms, then how just controlling the nature of the ylides we can control the stereochemistry of the product. Then we solved some questions based on that. Then we discussed about Peterson olefination reaction and how we can control the stereochemistry of the product just by controlling the reaction condition of this Peterson olefination and solved some question. Then we discussed about Julia olefination where we stated that we in this reaction we specifically get a E double bond. So if any product is given to you where the E double bond is formed, so the best route to get a specifically E double bond is this Julia olefination reaction. Then we discuss some question based on that. Then at last we discuss this rearrangement, Johnson-Claisen rearrangement, and stated how we can form a gamma delta unsaturated ester. Okay, so this much for today's class. Thank you everyone for attending my class. We'll meet in the next Sunday at the same time. Have a nice day.